So you're saying Ryan is asking about U as a function of PV led to du is equal to partial U by partial T at constant V multiplied by dt plus partial U by partial V at constant T multiplied by dV. This meant du is equal to CV dt plus pi t dV, where the whole idea was that pi t is 0 for an ideal gas, right? And you are asking what's equivalent for H. So for H, our variables that we used here were temperature and pressure instead of volume. So that immediately leads to dH. For those of you who are wondering what is this, ask Ryan Kane. If you're looking at the notes, okay, you can ask him on Slack. That's your name, right? Good. Now it's immortalized in the notes. So this will be partial H by partial T at constant P dt plus partial H by partial P constant T dP. One of these was heat capacity. That was this one, right? Cp dt. And this one led to Joule-Thomson coefficient. I mean, I don't remember what was the exact formula for it, but it came out of this manipulation. So that's led to, and this was also 0 for an ideal gas. So, okay. But now today, what we are talking about is we continue our discussion of second law of thermodynamics. And second law of thermodynamics, we have had two equivalent, we have many equivalent statements so far. One of them was that the total change, the change in entropy of the total system, which is total system, I mean system plus surroundings or an insulated system, must be 0 for spontaneous process. We had an equivalent form of this. So this could be written down as ds total is equal to ds system plus ds surrounding more than 0. We had an equivalent form that talked about only ds system. And that was known as Clausius inequality, which is again an equivalent statement of second law of thermodynamics. There is no new information in it. That says that ds system must be more than the heat given to the system divided by temperature. So you have gotten rid of S surrounding. This is only S system. So this tends to be more useful because you're no longer calculating S surrounding. The reason why you were able to get this is because S surrounding is related to delta Q. That's where it comes from. But now we are going to talk about even more useful forms, which today we will talk about even more useful forms of this. So let's call this equation number 1. Let's call this equation number 2. Even more useful forms of equation 2. By the way, no class on Wednesday. So day after tomorrow, there is no class. Use it to brush up on partial derivatives. Starting Friday, we will have lots of partial derivatives in the class. So if you are in any way feeling rusty about partial derivatives, total differentials, inexact differentials, go and brush it up, or it will get a bit clunky. So we are going to look at even more useful forms of equation 2. Why do we need more useful form? Because this delta Q is still, it's a path function. It's something external. So if we can express the second law purely in, so the idea is, can we express second law purely in terms of state functions of the system? That's what we would like to do. In order to do this, we are going to introduce two new state functions today, and both of them happen to be quite useful. The first one that we are going to talk about is called Gibbs. Some places just call it Gibbs energy. I like to call both of them as Gibbs free energy, and you will see a reason why it's called free energy. We will talk about Gibbs free energy, which is G, and that is defined as enthalpy minus temperature multiplied by entropy. And Helmholtz free energy, that is defined as, the symbol is A. Some places use the symbol F. The names for these variables change once in a while. The concept stays the same. I mean, the symbol changes, but the concept stays the same. A is equal to U minus TS. And for those of you who are mathematically advanced, you can go and read up that actually all of these state functions are related to a concept in math known as Legendre transforms. And we don't talk about that over here. If you take my advanced thermodynamics class in fall 2022, Chem 684, we talk about that a lot in that class, but we will not be talking about that over here. So this is advanced. So, but let's talk about this. And the claim that we are going to prove today is that equation 2, which is that ds system more than delta Q by temperature for spontaneous change is equivalent to saying that dg is less than 0 for constant temperature pressure process, and it is equivalent to saying that dA is less than 0 for constant temperature volume process. That's what we are going to prove. So notice that this was a more than something, but now, so over here we had a more than something, and in these two equations we have changed it to less than something, right? So let's prove this, and this is going to be extremely useful because now we have gotten rid of Q, we have gotten rid of anything related to surrounding. This is purely dg of the system, dA of the system. So let's try to prove this. So how do we prove this? First, let's look at, so we will start with equation 2. Equation 2 says that ds more than delta Q by temperature, right? I'm not going to write ds system unless I'm specifying it's the surrounding. Here it's obvious. Here we will remember that we are talking about ds system. So at constant temperature and volume, what can we say about delta Q? Can we write it as a change in a state function? Which one? Go ahead. du, okay, don't forget this one. At constant temperature and volume, delta Q is equal to du, right? So therefore, at constant temperature and volume, ds is more than du by T. This is equivalent to the second law of thermodynamics, right? Or Clausius inequality at constant temperature and volume. It's not going to be true in general, but at constant temperature and volume, we can get rid of the delta Q. So now if you think about dA, what is dA? dA is, so let's call these equations as equation number 3, the definition of G and A. I really don't understand why these IT people could not have given us bigger boards for this, or one board. Anyway, can you see from the back clearly? Okay. It would have been nice. So let's write down dA. What is dA? dA is d of u minus ts. What is that? du minus tds minus sdt. At constant temperature, what can we say about this one? Which of these terms will go to 0 at constant temperature? The third term, right? dt will be 0. So this is equal to, so this is true in general, but at constant temperature, we have dA is equal to du minus ts. So now if you look at this equation, this is telling us that at constant temperature and volume, du should be less than TDS, right? I take my temperature, I bring it to the left-hand side, and then I take du to the left side, right? So du less than TDS or du minus TDS negative, but at constant temperature, this is the same as dA, right? Therefore, dA less than 0. So we have just shown that therefore at constant, and we used both constant temperature and pressure. If we did not use constant pressure, we would have never been we use both constant temperature and volume. If we had not used constant temperature and volume, if we had not used constant volume, we would not have been able to use this equation, right? So if you're paying attention, you might have realized that in order to write this equation, we did not really need constant temperature, right? This one happens only due to constant volume. But over here, we needed constant temperature. Therefore, together, we need both constant temperature and volume. Therefore, at constant temperature and volume, dA less than 0 is condition for spontaneous change. And this is super useful because there is no path function here. There is no mention of surrounding. In fact, surrounding is always there. It's not that we have gotten rid of the surrounding. This applies not just for an isolated system. This applies for any system, irrespective of whether the work being done on it is reversible, irreversible, whatever path you are taking for the work. I mean, it does not depend. You will always have dA less than 0 for spontaneous change at constant temperature and volume. Okay, so this was the first proof. This was the proof for dA. Now let's go to the proof for dG. Any questions about this? Go ahead. Yeah, that's the thing I'm trying to say. It's kind of strange, right? For ds, we had greater than, oh, you're talking about this equal to. Sure, but you can be very rigorous, and that is also spontaneous change. But the reason I'm ignoring it is because technically I would call it as reversible change, right? Because if you use an equal to, then not just the forward direction is spontaneous, the backward direction is also spontaneous. You're absolutely correct. If you want to be rigorous, you can put equal to. So if I ask you condition for spontaneous change, and you answer ds more than delta q by t, or you answer ds more than equal to delta q by t, I would still give you full points. But if you said ds less than delta q by t, then I would not give you full points. I would give you probably negative points. Okay, it would make me very sad if you said that. So now let's try to look at dg, and it's a similar proof that's going to apply here. So now we want to prove that dg less than 0 for, what's your name? Say again? Alan. So Alan said we could also put a less than equal to here, right? It's the same idea. It's just that now the backward is also spontaneous. Here I'm just using inequality, but it's the same idea. For constant temperature and pressure, spontaneous change. How do we do this? Same idea as last time, our last proof. We know that Clausius inequality says that ds is more than delta q by t. What can we say about delta q at constant pressure? It is equal to d of what? H, right? It's the d of enthalpy. Therefore, ds more than dh by t at constant pressure, or dh less than tds, or dh minus tds is negative. So now let's go and look at dg, and if we see dg negative is the same as dh minus tds negative. So dg is equal to d of h minus ts is equal to dh minus tds minus s dt. We are talking about constant temperature and constant pressure. So once again, this term becomes 0 at constant temperature. And we don't have to worry about constant pressure in this equation because there is no pressure term. So this is equal to dh minus tds. Therefore, now you can see we got the same thing over here. dg less than negative is condition for spontaneous change at constant temperature and pressure. Okay, so this was the proof. What's more important than the proof is the message that you remember. What did we do here? So let's summarize all of it. All of these, what we showed here are just statements of the second law of thermodynamics. So we had the Kelvin and Clausius statement, which were wonderful, but these mathematical statements tend to be more useful. So let's recap all of them. Delta S total is equal to, let me use differential symbol. ds total is equal to ds system plus ds surrounding more than 0. So I'm writing down for spontaneous change conditions. Second law is nothing but conditions for spontaneous change. That's all second law talks about. So the first one is ds total is more than 0. I'm not going to number it. I will number it together. So, and this is an important list of equations because this is really a key summary of second law that we have so far. And we can call it equation number 4. When we don't want to talk about surroundings, then we can just talk about ds system. In that case, it is more than delta Q by temperature, and we have gotten rid of surroundings. Yet another equivalent statement is that dA is less than 0 if you have constant temperature and pressure process. It's not going to be true in general. Sorry, constant temperature and volume. And if you have constant temperature and pressure process, then dg is negative. All these 4 are equivalent statements of second law of thermodynamics. The last 2 are very nice because there is no surrounding, there is no path function. However, they are limited to certain specific types of processes. Any questions? Okay. So now I want to do 2 things. I want to give you a bit more physical intuition into A and G. What does it really represent? Why is it called free energy? Where does this term free come from? And the second thing I want to do is to get into Maxwell relations. So, and I'm debating which one to do first. Let's do Maxwell relations. Let's get started with it. So you have time to, it will get you a bit more worried about your partial derivatives if you're not worried, okay? It's important that you go start doing it. Otherwise, I will keep warning, do your partials, do your partials. I mean, the first time I taught this class, it became obvious that a big differentiator between the grades in this class was whether you had done calculus 3 or not, which is unfortunate. I wish calculus 3 was a prerequisite for this class, but then it's complicated. So that's why I keep warning you. If you haven't taken calculus 3, look at the math modules. And in the last year, I have seen many students. I can give you their names. You can go and talk to my undergraduate student, Fiona. She took this class without any calculus 3. She went through the math modules. She got an A+. If you go through the math modules, you can get an A+ in this class, even if you have not taken calculus 3. I promise you. But you have to go through the modules. You have to solve those problems, okay? So I will talk about the physical significance of the Gibbs free energy and the Helmholtz free energy probably on Fridays, in Friday's class. But today I want to get started with something more mathematical. And the first one is this concept of integrated first and second law. And of all the equations we have done so far in thermodynamics, this equation that I'm going to derive next is probably the single most important equation. If you forget anything and everything in thermodynamics, but you remember this equation, you can start and derive everything from it. It's like in organic chemistry, you know, there is this book in organic chemistry called Morrison Boyd. Does anyone know this book? No one? It's a cool book, and there is a chapter in it on alcohols where he says, the author starts by saying that if you're lost on an island and if you have no other chemical, only if you had ethyl alcohol, you could recreate every chemical starting from ethyl alcohol. You could keep starting and recreate everything. Also, as you're recreating, you could also have a good time because you have ethyl alcohol, right? So this equation is like that. You can create all of thermodynamics out of it. So what do I mean by this? Our first law of thermodynamics says, and this equation is also a precursor to doing Maxwell relations. So our first law of thermodynamics says du is equal to delta Q plus delta W. But we know that du is this magical thing. It's a state function, right? It doesn't depend what path you are going to take. So you could have very well written it as du is equal to delta Q reversible plus delta W reversible And both of these DUs will be the same, right? If you're going from point A to point B, it does not depend. If endpoints are same, it does not matter which equation you use. It's always going to be the same. So now let's call this as equation number 5, and let's call this as equation number 6. If equation 5 and 6 are the same, then in equation 6, we can do further substitutions, right? Let's say we are doing only pressure volume work. Then what can we say about delta W reversible? Go ahead. Delta do this one. What should we write about it? And should I call a P external or just P? But it's reversible. No, reversible. I'm writing equation 6. When it's fully reversible, then the nice thing is I can write delta W reversible as minus PdV, right? I don't have to worry about P external because it's a reversible process. So the pressures are the same. What can I write about delta Q reversible? Can I relate it to entropy? Go ahead. TdS, right? So this equation I derived from equation 6, but it doesn't matter whether the change in U is coming from a reversible process or an irreversible process, right? You can equate 5 and 6, and TU is equal to TdS minus PdV is true in general. It is always true, irrespective of whether you changed U through a path function, through a reversible process or an irreversible process, it is always going to be true. And this equation, what you have done is to integrate, you have integrated the first law and the second law of thermodynamics in the same equation, right? In order to get this equation, you started from du is equal to delta Q plus delta W. But at the same time, you equated delta Q reversible is equal to TdS. That is an equivalent statement of the second law of thermodynamics. So this equation includes both first and second law. And it is my favorite equation in thermodynamics because it includes everything. It's just awesome. If you forget anything, you can start from here. You can pretty much rederive everything in this course from this equation. du is equal to TdS minus PdV. So notice something happened here. If I think about this equation number 7, what are the variables as which I'm expressing U as a function of? Go ahead. Are you sure? Look at the things that are being differentiated. Let's go back to what we started today's class with. In this case, what was U a function of? Temperature and volume, right? Because you have dt and dv, so U is a function of temperature and volume. For enthalpy, you have T and P, so enthalpy is a function of temperature and pressure. So in this case, what is U a function of? S and V. This is very important because this means that S, V are natural variables. And this is a term I am not using loosely. It's got a very specific meaning. S and V are natural variables for internal energy. Natural variables are a concept that Atkins and most PChem books do not really talk about. I don't know why. You have to go to graduate thermodynamics to really think about this carefully. And I don't know why. If I wrote a PChem book, I think I would really talk about this in detail because it's so important and it simplifies, hopefully, things from here. Why do we call this natural variables? The reason we call this natural variable is because earlier we wrote U as a function of temperature and volume, right? That's fine. We got an equation. We could have very well written U as a function of temperature and pressure. No one's stopping you from doing that. You could write U as a function of temperature and enthalpy. The problem with all of these is that when you write it in this form, you are not including all information from the first law of thermodynamics and the second law of thermodynamics, okay? So these representations are not complete in information from first and second law. They are missing something. The only equation for U that has included both first and second law at the same time is when U is written as a function of S and V. Now, this is true for a constant composition system. Remember, we are not talking about N. We are not changing the number of species. Starting next week, we will start talking about variable composition systems. And there we will see that actually, so starting next week, for variable composition, when N also varies, we will talk about something called chemical potential, and then we will see that the natural variables for U are S, V, and N, the number of species in the system, the different number of species that you have. How much of oxygen do you have? How much of carbon dioxide do you have? But for now, the natural variables for U are S and volume. Okay, so don't forget this. This equation, if I just wrote down this equation for you, PU is equal to TdS minus TdV. At first sight, it looks like, where did it come from, right? It looks quite complicated, but if you take a moment and go back, just remember du is equal to delta Q plus delta W. du is a state function, and if you are thinking only about pressure volume work, then we can write this as delta Q reversible plus delta W reversible. And if you are only thinking about pressure volume work, delta V W reversible becomes minus PdV, and it's a reversible heat change, so this becomes PdS. And this equation is super easy to derive. That's also another reason why I like it. If you forget this equation, that's okay. You can just derive it if you remember first law and this second law. And it's very important because it includes all information. Later, I might give you a problem in one of the homeworks where I would show you how, if you, I can make it mathematical as to how much information do you lose if you don't start from this equation. But hopefully you get the gist of it. This form includes both first and second law. I'm mathematically not proving as to why you cannot have another form of U which includes both, but hopefully you get the flavor. So yeah, I mean, I cannot emphasize how important this equation is. So I will make a heart sign over here and I will draw an arrow through it. And this equation should be your best friend forever. Okay, it's very, very, very important. Don't forget this equation. If you forget Maxwell relations, which many of you will, I forget them. You can start from this equation and derive every Maxwell relation in 10 minutes without any problem. You won't have to worry about remembering things. Even in the final exam, you will be allowed a cheat sheet. And one of the things you should always put on your cheat sheet is the Maxwell relation. It saves time. So let's get to our Maxwell relation, starting from this equation. Okay, so equation 7. Equation 7 says du is equal to TdS minus PdV. And I'm saying that this is the same as, basically we are saying that U is a function of S and V. Okay, now pay attention. I'm going to do some mathematical wizardry, okay? Some like magic. So if U is a function of SV, what can we say about du? How else can we write it? We can write it as partial U by partial V at constant S multiplied by dV, right? Actually, let me write down the other side first. Sorry about that. So we can directly compare it. So I can write it down as partial U by partial S at constant V multiplied by ds plus, this was equation 7, plus what should be the second term? Partial of U with what? V at constant what? S dV. Now we can do something very interesting. We can compare equation 7 with equation 8. If we compare equation 7 with equation 8, we reach the conclusion that these two things must be equal. And these two things must be equal. Right? So what we have just shown is that temperature must be equal to partial of U with partial of S at constant V, and pressure must be equal to minus partial u by partial v at constant s. This equation is the most fundamental definition of temperature. When we do graduate thermodynamics, we define temperature as here. I'm showing you that temperature is equal to this, but you could start your thermodynamics by defining your temperature this way, as to how does the internal energy change with respect to entropy at constant volume. So suddenly you're looking at some partial derivatives that look very strange. I mean, u with v at constant entropy, what on earth does it mean? If I removed everything and asked you to just derive this equation, you'd probably scratch your head, right? Like, I don't know how to do it. If I had hair, I would pull it out. I don't know how to do it. But whenever you get lost, start with that equation, d is equal to TdS minus PdV. In this case, if you start with this equation, you can derive this in 1 minute. It directly follows out of it, right? We are not quite at Maxwell relations, but these equations are very useful. We are going to be using this in a variety of ways. So, I mean, I warned you, right? We are getting heavy into partial derivative land. So get ready. Now let's get to Maxwell relation. There are 4 Maxwell relations, and this is the most famous Maxwell that we have all known of in context of electricity, for example, of Maxwell's laws of electrodynamics. It's the same Maxwell who was also doing thermodynamics. So Maxwell relation says, it really follows from a very basic properties of partial derivatives. Maxwell relation says that if you have a function f, any function, okay, I will write down where it comes from, calculus, and then we will go and look at equation 7 and derive our Maxwell. We will look at equation 7 and derive our Maxwell relations. But first, let's look at it very generally. If you have a function f of xy, we can always write it as something multiplied by x plus something multiplied by y, right? So let's say it is g multiplied by dx plus h multiplied by y. So in general, this g will be some function of x comma y multiplied by dx plus h as a function of x comma y multiplied by dy, right? So in order for such an relation to exist, you can show using calculus, one must have partial g by partial y at constant x is equal to partial h by partial x at constant y. So partial g by partial y at constant x and partial h by partial x at constant y. This is the condition for a total derivative to exist. I think it's got a name, Euler's relation or something like that. Doesn't matter, but remember the equation, okay? For example, it's easy to show, for example, that let's consider an equation where it is true. So let's give me a f of xy. Can someone give me a simple f of xy? Huh? Okay, what's your name? Awesome. Now you stay with me, okay? Let's write down df. So we know that df should be partial f by partial x at constant y multiplied by dx plus partial f by partial y at constant x multiplied by dy. So what is partial f by partial x at constant y? 2x dx. And what is this one? 2y dy. So in this case, what is g? G is 2x, right? And what is h? 2y. So let's see if our condition is followed. What is partial g by partial y at constant x? Tell me. If this is g, What is partial g by partial y at constant x? 0. What is partial g by partial x at constant y? 0. So it's true, the relation between, go ahead. Oh yeah. Oh. Good, you're all paying attention. Good. So this is for one function. You can write down any function you want, right? Go and multiply it by x squared cos x plus y squared hyperbolic tan of y to the power x. I don't care. Works with this, you will find this to be true. At the same time, if I gave you an equation where it is not true, where it looks like f of xy is equal to something multiplied by dx plus something multiplied by dy, like g or h, where partial g by partial y is not equal to partial h by a partial x, then this f won't be a total derivative. So proving this relation is hard. Using it is very, very easy. Okay, if you go through the math modules, I have lots of examples for this. If it looks confusing to you, that's why we don't have well, I have to give a talk, but that's another story. You can go through it and please become comfortable with it. If you're comfortable with this relation that I wrote over here, then Maxwell relations are going to be trivial. If you know this relation, and if you know the first and second integrated first and second law of thermodynamics, all 4 Maxwell relations are really, really easy. But if you are not comfortable with either of these two, this class is going to become harder. So let's use this and let's go to equation 7. Equation 7 says du is equal to TdS, and I'm going to write it this way just to make our life simple. Everyone happy with this? Anyone unhappy with this equation? Speak now or hold your tongue, whatever. What is it? What you say when people are getting married? Yeah, speak now or forever hold your peace. Great. Can we apply Euler's relation to this one? We know u is a nice function. It is a state function, so we should be able to do that. So if we take temperature, partial temperature, differentiate it with respect to volume at constant entropy, that should be the same as minus partial of pressure differentiated with respect to entropy at constant volume. And this is our Maxwell relation number 1. It looks super strange. Yes, very strange. We will see. So these relations happen to be very, very, very important. A lot of, for your second midterm, I will be giving you some papers which actually apply thermodynamics to very practical problems like climate change or protein folding. And you will see how directly Maxwell relations allow us to manipulate experiment done at one conditions and talk about some other property at some other condition. So this is our first Maxwell relation. There are 3 other Maxwell relations, and they all follow from writing dH as a partial derivative. That will give us a second Maxwell relation. dG's total differential property and dA's total differential properties, right? So UGHA, all 4 lead to 4 different Maxwell relations. Now they are so important that if you go on the internet, you will find mnemonics to remember them. There are lots of arrows joining here and there. You can do all that, or you can just become very comfortable with the integrated first and second law and with this Euler relation regarding partial derivatives. Okay, so let's move on to the second one. Let's go to G. Second Maxwell relation. So dG, so we have G. What is the definition of G? H minus Ts. So we have some new material in the last 2 classes. Okay, I don't expect everyone to immediately jump into G is equal to H minus Ts. It will require some memory to remember that G is equal to H minus Ts, just like H is equal to U plus PV required some memory, right? So it takes some time to remember these things, practice through it. So let's work through this. So therefore DG. So first we have to, and so Maxwell relations always arise from writing the state function in its natural variables, right? I did not come up to a Maxwell relation by writing, I could have tried to write a Maxwell relation from this equation, right? Du is equal, I could have written down a similar thing over here, right? The same Euler relation could be used over here, but that won't be Maxwell relation because these are not natural variables for U. Maxwell relations happen, Maxwell relations, and this is something barely any book emphasizes. I've not seen an undergrad book especially emphasizing this. Maxwell relations come from using Euler's relation for total derivative on state functions in natural variables. Okay, so you must have it in natural variable. If you don't have it in natural variable, it won't work. So first we have to figure out what are the natural variables for G. Can anyone tell me what should be the natural variables for G without doing algebra? Any ideas? Go ahead. No, it will be pressure and temperature. It kind of makes sense, but let's see how it works out. For A, the natural variables should be V and T. Why should you have guessed this? Where have you seen hints for this? Go ahead. Yeah, we saw this when we wrote down the equivalent second law of thermodynamics, right? We saw that A is constant temperature and volume. G is constant temperature and pressure. So this is hint that maybe this is something special about these variables for G and A, but we haven't shown it exactly. Let's do it now. So dG is equal to H minus Ts. G is equal to H minus Ts. Therefore, dG is equal to dH minus TdS minus SDT. That doesn't help us in any way, but we know what is H. H is U plus PV, right? So this is D of U plus PV minus TdS minus SDT is equal to du plus PdV plus VdP minus TdS minus SDT. Oh no, so messy. What do we do now? Can we cancel a few things? Go ahead. I haven't said that yet. I want to be very general. Use the integrated first and second law. What does that tell us about du? It tells us that du is TdS minus PdV, right? And plus this other stuff, plus PdV, plus VdP, minus TdS, minus SDT. Now a few things cancel out. TdS minus TdS, minus PdV plus PdV, and suddenly we are left with VdP minus SDT. dG is equal to VdP minus SDT. This is equivalent to the integrated first and second law of thermodynamics. And therefore, the natural variables for G are pressure and temperature. These are natural variables. So from this, we can again lead to a bunch of relations. We could have written down dG as partial G by partial P at constant V multiplied by dP plus partial G by partial T at constant P. No, I totally messed it up. It's pressure and temperature, sorry. dt, right? If G is a function of pressure and temperature, this will be true. What does it tell me? Therefore, this we should be able to equate, and this we should be able to equate, right? That's not a Maxwell relation, but that's another identity. It's as soon as you get to first law and second law of thermodynamics, that's why I called it like an ethyl alcohol. All of a sudden, you can start creating thermodynamic identities out of nowhere. And they're just so powerful and so beautiful. They almost look alien, but they're very powerful. So therefore, partial G by partial P at constant temperature is equal to volume, and partial G by partial T at constant pressure is equal to minus times entropy. They don't have a name. They are just identities. And I could create, you will have final exam problems where I will just ask you to say, prove that partial G by partial T at constant P is equal to minus S. One of you will raise hand, ask ideal gas or not. I will say no in general. And then you will be like, how do I do it? Start with your integrated first and second law and it will follow through. Okay, don't try to commit these things to memory. It won't go well. It's a bad idea to try to commit these things to memory. There are just so many. Okay, what you should commit to memory is du is equal to TdS minus PdV. That is the important equation. After that, everything follows. So we don't have a Maxwell relation yet. Let's call it equation number 10. And I will stop. The other two Maxwell relation I will do in Friday's class. So equation number 10. Equation 10 said that dg is equal to vdp minus sdt. Oh, by the way, this equation is so useful. I just wrote a paper in which, does anyone know what's a polymorph? No one knows what's a polymorph? Go ahead. So you don't know what it is. A polymorph is when a crystal can exist in two crystal forms, when a material can exist in two crystal forms, okay? So, yeah, I mean, since you are not, I thought all of you will be like, yes, we know what's polymorphs. So my story is useless. I will just skip it. What's the point? It's okay. Let's go to dg equal to vdp minus sdt and derive our Maxwell relation. So can anyone help me write down a Maxwell relation from it? Remember this equation. Ryan, you have answered many things. Someone else. Someone from the back. Go ahead. There we go. That's your Maxwell relation. Number 2. Okay. Again, don't try to remember it. You can use the mnemonics on the internet. They're like complicated. I think I can. Yeah, I don't use the mnemonics. Try to get the concept, and it's easy to derive. For your exam, for in your cheat sheet, you can write it down, at least in this class, but otherwise try to remember the concept where it came from. G has its natural variables, pressure and temperature. And once we applied Euler's relation to this, we get our Maxwell relation number 2. So when you go home today, I want you to look at dA, which is d of u minus ts. And I want you to look at dH, which is d of u plus PV, and derive Maxwell relation 3 and Maxwell relation 4. Do it on your own. I will do it in the class, but I really, really, really sincerely beg you to do this on your own. There is no point at all in copying it from the board if you don't do it on your own. Please do it on your own. You can go and compare. You can treat it as a practice problem where the answer is everywhere on the internet. You will be able to get it out of Wikipedia. Just compare without trying, just close everything. Just start from these two and derive Maxwell relations similar to what we did for G and U, and see if you get it right. Okay, if you get it right, you can give yourself a pat on your back. You are in good shape. So next time, no class on Wednesday. On Friday, we will do Maxwell 3 and Maxwell 4. And then, so no class on Wednesday. And then I will tell you why are G and why are Gibbs and Helmholtz called free energies. And next week, we will start talking about variable composition systems. Hi.
I have a question.